here's a quick video in case you missed class, or if you want to go back and brush up on these topics. This is about rationalizing denominators, and I guess in the next part of the video, simplifying square roots. So first, rationalizing denominators. The background on this is that typically, right, the convention and the expectation is that you're not really allowed to finish a final answer with a square root in the denominator, or for that matter, anything irrational, okay? But, well, let's just stick with you're not allowed to have a square root in the denominator. It's just not good manners. So that's the pretty common convention, because don't forget that numbers like the square root of 3 and 4 root 2, those numbers are irrational. And so that's why it's really known as rationalizing the denominator. It's like make this irrational denominator into something that is rational. So, rationalize it. But here's the thing. If you have any plans whatsoever on taking one of the AP Calc exams, at this time, 2018, they don't really expect you, they don't require you to leave your final answers with a rationalized denominator. Like, they're okay with a final answer like this or like this. So I guess to a large extent, I'm going to be okay. We'll let that kind of like dictate and drive my expectations, I guess, that, the ultimate AP exams. But so I will not expect that for full points on a test or something. I'm going to be okay with final answers like this or like this. But there are reasons, and it's not really only about you might have a professor one day or another math teacher or something, or that expect this of you. Another reason I just thought of was if you're taking the SATs and you get this as an answer, but and it's correct in a way, but it doesn't match any of the choices because all of the choices have rationalized denominators. That's another reason. So, but look, even for my class, you should be aware of such things as one. I know I'm getting ahead of myself, and you don't need to write this down, but even for my class, I'm just going to say really quick that you should be aware that something like 1 over root 2 is equivalent to root 2 over 2. You should know that they are equivalent, and you should understand why, basically. So, I don't know. So I'm really only letting you off the hook to a certain extent. But here we go. Just a kind of quick review on how we rationalize denominators like the square root of 3 and such. So, how do we make the square root of 3 into not a square root anymore? What do we do to it? How can we rewrite this fraction in the way we want? Well, cutting to the chase, if we multiply root 3 times root 3, like multiply it by itself, it's not going to be a square root anymore. We'll see that happen in a second, but first, don't forget that I can't just do that. I can't just multiply the denominator by root 3. In order to make everything cool, I also need to multiply the numerator by root 3. Okay? And the full story there is technically that means you're multiplying that fraction by 1. Root 3 over root 3, that's really just 1. And you're totally allowed to multiply something by 1 because it won't change its identity, right? Remember, multiplying something by 1 is still going to be the same thing. Anyway, so numerator times numerator, doing 5 times root 3, well, that's just going to be 5 root 3. Can't really do much there. And what's root 3 times root 3? Well, that, at least for starters, that is root 9. You could say that's root 9, but what's root 9? 3. So see how that works out? And that works beautifully like that, like for all stuff like that. Like another example is if you were going to do root 7 times root 7, that's going to end up being just 7. And root 11 times root 11 is just going to be 11. So moving on to the next example. Again, just to kind of get rid of all the square root, all you really have to do is multiply that bottom by root 2. But you also got to multiply to the numerator, and so 1 times root 2 is just going to be root 2. And then when you multiply 4 root 2 times root 2, these will multiply together to just get what? What's root 2 times root 2? Well, that's just going to end up being 2. So maybe I'll just write out a quick little baby step. So the 4 has yet to be multiplied anything, and these two multiply together first, but to get 2. But for my final answer, 4 times 2 is, of course, 8. And once the denominator has been rationalized, then you're done. This example is a little bit different because if you were to actually see what happens if you just multiply the bottom by root 5, because you might, I don't blame you for thinking that right now, especially if it's been a long time since you've reviewed this. I don't blame you for thinking that, well, all we got to do is multiply the bottom by root 5, right? Well, if you think about what that would mean, if you were going to multiply the entire bottom by root 5, that would mean distributing. And, this square root would kind of go away, but you'd end up creating another one. So anyway, the bottom line is that won't work. Do you remember what does work? To rationalize a denominator like this where there's 2 terms? Well, to cut to the chase, that's what actually does the trick. If you multiply 3 plus root 5 times 3 minus root 5, it's just going to work out. It's amazing. Don't forget that you also got to do that to the top to make everything, legit and kosher. So let's take care of the top first. Now remember, to multiply this numerator times this numerator, we've got to do the distributive property. So 4 times 3 is 12, and 4 times negative root 5 is just going to be minus 4 root 5. And so that's my numerator there, and it's, like I guess I haven't said this yet. For some reason it's okay if there's a square root in the numerator, just not the denominator for some reason. Double standards. But here's what happens on the bottom. What happens on the bottom? You got this denominator, this binomial, times this denominator binomial, which isn't that going to be FOIL? So if we do firsts, outers, inners, lasts, we end up getting 9 for 3 times 3. Then 3 times negative root 5 is negative 3 root 5. Then the inners, we get plus 3 root 5. And then for the last, we get positive root 5 times negative root 5. So root 5 times root 5, that's just going to end up being 5. But, it's a positive times a negative, so that's a negative result. And so negative 5. Now, the reason why this works like a charm is because look at these 2 terms that combine as like terms. Negative 3 root 5. Like, we still have square roots, right, in the denominator, but not for long, because this term and this term add up or combine to be 0. So now the numerator is what it is. And the denominator, these 2 terms are gone, so yay. And then we have 9 minus 5 to be 4. So the denominator has been rationalized, but as I look at this, I realize that this can actually be further simplified. So you should always want to leave your final answer in the simplest form possible. And when you look to divide the 4 into this numerator, remember that you have to divide the 4 into both this term and this term, but you totally can. Okay? If I was going to really break down all the steps, maybe I could write it out like this first. 12 divided by 4 minus 4 root 5 over 4. Remember? Dividing this 4 into both terms. And so this just becomes 3, and this just becomes root 5 when the 4's cancel out. Okay? And that's that problem. Little extra twist at the end. So we rationalized to get to here, but then you should have noticed, or you should, that's expected of you to notice this kind of stuff, that this can be further simplified. So plot twist at the end there, more work to do. Changing gears, the other topic to review in this video is just simplifying square roots, right? And this is definitely expected of you for like a final answer. If a square root can be simplified, you should simplify it. That's just an expected convention, okay? So before I start actually doing this, there are 2 very common ways that I know of. One way I prefer more than the other, and I usually say that there's the way that I prefer, and then there's the way that Mr. Berchanowski prefers. So first, my way, I'll show you both ways. My way involves looking at the square root of 12 and thinking to myself, can I do the square root of 12 cleanly? And the answer is no. 12 is not a perfect square. Hey, speaking of Mr. Berchanowski.
Oh, hi there. Maybe I can help with this problem.
I believe you can. Nice shirt.
Thank you. I'll be doing some refereeing a little later. Square root of 12, one of my favorites. I personally, when doing the square root of 12, like to make something I call a factor tree, Mr. Falk. So we want to look for prime factors of the number 12. Mr. Falk, I'm going to question you like you were a student. What is a prime? Give me some factors of 12.
Prime factors or
any type of factors you would like, friend.
3 and 4.
All right, so let's break 3 down, or 12 down to 3 times 4. Nice looking 4. I also learned from a great student I call the Kuhnhahn method, because anytime you have a prime factor that can only be broken down into itself and 1 as the factors, we like to underline it. Mr. Falk, 4, a little bit of work up there.
That's got to be 2 times 2.
Oh, the ballerina special, 2 times 2. Very good. So we have 3 factors, which is, in order for me to pull a number out of inside of that square root, I have to have 2 of that number. Do I have a pair of any numbers, Mr. Falk?
You have a pair of 2s, Mr. Birch.
Oh, so let's pull 1 2 out. The only guy who doesn't have a partner is that lonely 3. Now, I know you like to do it a different way, and mathematically it's a nice way. But if we had to bet, 60% of the time, students will use my method every time.
That does make sense. Hey, stop hitting me. Bye.
Bye, guys.
How long are you going to be here?
I have to go ref.
Okay.
So I'm out of here.
Okay.
Cut grass.
All right.
See you, buddy. Bye, America.
All right. That was fun. So that was actually Mr. Berchanowski's way. So gave that to you first. And as far as my way that I like to do, the other way, and it's always going to be your choice, whatever way you want to do. What was I saying? So my way involves looking at the square root of 12, and you can't do the square root of 12 cleanly. It's not a perfect square. It's not like doing the square root of 16 or the square root of 81. Square root of 12 you can't do cleanly, but maybe there's a piece of it that you actually can do cleanly, right? So maybe I can break it up into a number that I can take the square root of cleanly, and then whatever else is left over is left over. So my way involves rewriting it as a couple square roots, and I'll ask you right now to think about it. Is there any perfect squares I can break off of 12? And maybe you came up with 4. And so I'm going to rewrite square root of 12 as the square root of 4 times the square root of 3, because I can do the square root of 4. What's the square root of 4? If we can do it, let's do it. It should be 2. And that's really all I can do. That's all the square rooting I was able to do. And notice how my answer matches Mr. Birch's answer. And so both ways work. Little ending note, side note on my method is, I could have broken this up as root 6 times root 2, right? Root 6 times root 2. But that wouldn't have gotten me anywhere because, I can't do that and I can't do that. So I wouldn't break it up like this, even though that's a legit way to break it up. I'd have to break it up into something I can actually do as one of them. Okay, so let's do a couple more, I guess. So Mr. Birchanowski would start to break this down into whatever. It doesn't matter. You could do 6 and 3. You could do 9 and 2. So let's do 9 and 2. And 2 cannot be broken down any further, so I guess we underline that. 9 can be broken down into 3 times 3 only, and those both can go no further. So it turns out that these are my final prime factors. Are there any pairs? You bet. So there's a pair of 3s, so you would bring 1 3 out, and any singles would remain under the square root. So 3 square root of 2. My way would involve breaking it up into a perfect square and whatever its partner would be. Now I'll say this right away now. You want to find the largest perfect square in 18. So what a coincidence. I'm going to actually, again, break it up the same way into root 9 times root 2, because I can do root 9. Okay. See, Birch's way, you could have started it off as like 6 and 3, and it wouldn't have mattered. You would have ended up with the same final prime factors. Okay. So again, 9 and 2 is fine for Birch's way. 6 and 3 would have worked out fine, but for my way, it's got to involve a perfect square like 9. So this is the only way to go for my way, because it's one break, right? For my method, it's just one break, and you do whichever one you can do. And in this case, I can do that, and so I do it. That's just 3. See, again, at least I'm doing some square rooting. I can't do the entire root 18, but at least I can do root 9 to get 3. Unfortunately, I can't do it all, and so root 2 just remains root 2. One more example. So first, Birch's way. Let's start with 8 and 4 to make 32, right? And this would be then 4 times 2, and so that's done. This 4 would have to be 2 and 2. This 4 can break up again into a couple more 2's. So here we go. Now we look for pairs if you're doing it this way. We have one pair of 2's, right? So that's a single 2 that comes out. Then we have another pair of 2's, and so another 2 comes out. And then we have a single 2, which must stay underneath. So on the outside, we can multiply those together to make 4, which makes the final answer, 4 root 2. If you're doing it my way, you're looking to break it up one time, right? And you want to break off the largest perfect square that there is in 32. So even though, this is why I'm doing this example on this review page, right? Because you could break off a 4, but 4 is actually not the largest perfect square that you can break off of 32. What is? 16. And so I can do the square root of 16 to just get 4. And so final answer, 4 root 2. And yep, that is it for that.